Hello, beautiful people, and welcome to this episode. Today, we are reviewing for the AP Chemistry exam, specifically looking at Unit 4 on chemical reactions. And it's kind of a grab bag of different topics, although there are some general concepts that carry throughout. And it should be noted that as we look at a list of these types of reactions occur in all units 1 through 9 in AP Chemistry, although here they're kind of tucked into one nice little place in Unit 4 so we can see them all together. So I hope you're ready to look at some reactions, and if all goes according to plan, in a few moments you're going to be totally prepared to ace your AP Chemistry exam. So let's get started. Unit 4 begins with an introduction for reactions, which, if you go check it out, you'll find it talks about a lot of physical and chemical changes. That also appears down here in section 4.4, so I thought we could handle both of those together to kickstart this video. Okay, so it's a good way for us to think about whether a reaction is occurring or whether it's not occurring. All right, here's a couple of definitions. Hopefully you know them, but if not, feel free to pause the video and write them down. A physical change is a change in which no new substance is produced. That's the criteria. There are a number of physical changes out there, but the key is whether you're looking at a reaction or a model or a drawing of some kind, we're not making anything new. That's a physical change. So examples include phase changes. These get a lot of people all mixed up. They have fancy names like melting, boiling, freezing, condensing, and sublimating. And it looks like something's happening when those things are occurring, but you got to have laser focus. Those are not chemical changes. You're just moving molecules around and separating them and combining them. Temperature changes, where no new substance is produced. Yes, you're heating them up, cooling down. Shape changes, like crushing, flattening, just generally messing with your material but not making anything new. And dissolving. Okay, dissolving also throws a lot of people off because it really looks like something's happening. You throw it into the beaker with water in it and it disappears and it looks like something new is made. But no new bonds are actually being formed between those ions. The water molecules are surrounding the ions, but they're not forming any new bonds or new substances. On the other hand, a chemical change is a change in which a new substance is produced. So whether you're looking at a reaction or a particulate model, if you see new groupings of atoms or molecules, that's a chemical change. So examples include breaking and forming chemical bonds. If you see that happening, new formulas being formed, or in the models, the things are grouping together. Gas productions, gases forming out of nowhere are a good indication of chemical change. Precipitation reactions, energy changes with no input. So if you mix two things together and there's an energy change, that usually means some bonds are being broken and formed. And of course, new substances, anytime you see new substances. Let's look at a couple of questions that involve chemical and physical changes. We'll start with this one. It's more a word question. Which of the following describes the changes in forces of attraction that occur as H2O changes phase from a liquid to a vapor? Again, phase change is a physical change, so we're not breaking any chemical bonds. And so we have to weed out the choices that produce or talk about bonds. HO bonds breaking? Nope, that's not going to happen. Covalent bonds between water molecules are broken? No. Between the water molecules, they don't have covalent bonds, they actually have hydrogen bonding. And ionic bonds between hydrogen and OH are broken. That's not true either because it's a covalent compound. The correct answer here is B. Hydrogen bonding between those H2O molecules are broken. So that is our choice. So physical change, no new substances are being made. Next up, we have a couple of models to look at. And you can go ahead and pause the video if you want. We'll do one and then I'll do a pause the video with you. So here we have a mixture. The reactants represented above are placed in a vessel and a reaction occurs. So they tell us a reaction occurs. Which of the following best describes the contents of the vessel after the reaction has proceeded as completely as possible? Okay, I tell my students when you see a question like this with a particulate model, the first thing you got to do is start counting. Just start counting, take inventory of what you got. So I've got two of these molecules, which I recognize as methane, carbon, and 4 hydrogens, and some oxygen molecules. Remember, oxygen is diatomic when it's by itself, so you got to have them in pairs. Okay, so I've got two of those and 6 oxygen molecules, or 12 oxygen atoms. My answer has to have the same number of atoms in it. That's the key. So I know that the reaction is going to occur, and I do know that when methane reacts with oxygen, it's actually going to make carbon dioxide and waters. Okay? So I'm looking for a reaction in which the methanes have turned to carbon dioxides and so on. So I'm looking for some CO2s. There's a couple right there. And some water molecules. So that's great. Now with 2 carbons, I have enough to make 2 CO2s. So I'm looking for an example that has 2 CO2s. That includes this one and this one. This one has 4 CO2s in it. I don't have that many carbons, so that's out of the question. So I'm looking probably at one of these two. So I've got 2 CO2s. I also have 4 water molecules I can make with those 8 hydrogens. So 2 CO2s, 4 water molecules, and they both have 2 CO2s and 4 water molecules. The difference is this one has a couple of extra oxygens in it. And so there are a couple of oxygens. If you start grouping these, and in fact, I highly recommend, messing up your paper a little bit, saying, okay, these are going to group together, and you can just kind of sketch groupings in there. We'll get carbons and carbon dioxides doing this thing. There are some extra oxygens, and so my correct answer is letter C. So feel free to mark up your drawings just to keep track of things. All right, it's your turn. Here we have nitrogen and hydrogen molecules, again, both diatomic, and a reaction is going to go. Which of the following would represent the results if the reaction were to proceed as far as possible? So take a moment. We have noted that we have 3 nitrogen molecules and 3 hydrogen molecules, so 6 atoms of each, and they're making NH3. So let's scoot this up so you can see the 4 choices and which one of those 4 choices is appropriate. All right, and if you chose D, congratulations, you did it right. So we have 6 hydrogen atoms. That's enough to make 2 NH3s, and that's what I got here. There's going to be some 4 nitrogens left over as a couple of diatomic molecules, and that is, again, a chemical change happening. All right, and this one is a big one, so I did it on 2 separate pages. Which of the following particulate diagrams best shows the formation of water vapor from hydrogen gas and oxygen gas? So forming water from oxygen and hydrogen. Here are our 4 choices, and we'll scoot them on there. All right, so we're forming water molecules. So here we have 6 water molecules, and I have 6 oxygens and 6 hydrogens. So that's not correct because I'm going to need 12 hydrogens. Again, 6 water molecules. Great, I have 6 oxygens and 12 hydrogens, except that's not the correct answer either because they're not diatomic. You got to remember those 7 diatomic elements. Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Down here, we have some diatomic oxygens and hydrogens, which is great. In order to make 6, I'm going to need 3 O2s and 6 hydrogens, and that turns out to be my answer. In the letter D, there's too many oxygens. There's going to be some left over that are not shown over here. So again, you have to count, you got to take inventory and make sure your final answer matches the number of atoms in the original answer. Up next, we have section 4.2 on net ionic equations. And we hit them early, we hit them often, and to be honest, most of the time, if you're asked to write a chemical reaction on the AP exam, they will ask you for a net ionic equation rather than a complete chemical equation. But let's start with the difference between the two of them. Complete chemical equations are the ones we start out learning about. They show the complete formulas for all reactants and products. And that works great as we're beginning chemists and moving along. Then we get into net ionic equations. Net ionic equations are what happens when we show only the active participants in the reaction. We might dump a bunch of stuff together and only some of them do anything, and the other ions or atoms or molecules that are there are just not participating. They're spectator ions. I lovingly call them loser ions because nobody wants to hang out with them at this point. I should make a quick side note. For all of these topics, if you look in the Unit 4 playlist, you'll see a whole bunch of videos with more detail on each one of these things. So if you need more practice or detail, head over to the playlist and check it out. All right, these equations omit spectator ions, which are present in the surroundings but not active in the reaction. Okay, so how do we do that? Here's a set of steps that I wrote for doing this for a net ionic precipitation reaction. This is usually the kind of reaction we learn about net ionic equations for. And so this is what I have come up with. So first, we want to predict the products. First, we have to start with the balanced chemical equation, see the whole thing that's there, and write their correct chemical formulas. That's step one. Okay. Then we're going to decide if this is a precipitation reaction, for example. We're going to decide which product, if any, will be insoluble. Give this compound a solid so we can tell it for later. Give all soluble compounds aqueous. This is the most important one. Anything that's aqueous is soluble, and if it's ionic, it has split apart into its ions, and we have to write them like that because that's how they exist. That's their truth. We have to honor their truth that they're ions. Split up all the soluble compounds into separate ions. Make sure to write the charges. That's important. Whenever you split apart and write a net ionic equation, please, please, please remember to put the charges on. Not for me, but for you, so you don't lose easy points on the exam. If it's an ion, it has to have a charge. Keep the insoluble compound together, though, because if they're a precipitate, those ions have found each other, they formed a lasting chemical bond, and they are together, so we should write them together. Cross out any ions that are separate and soluble on both sides of the arrow. These are spectators. So separate and soluble on both sides of the arrow. Write the remaining reaction, including the ion charges. Let me show you an example that I have prepared. It's a nice one that we often start with. So let's say I took some salt water, aqueous sodium chloride, and added it to some silver nitrate, which is also aqueous. Nitrates are always soluble. And another quick side note, please take some time before the AP exam and review your solubility rules. Which ions tend to be soluble and which ions tend to not be soluble. You will not be given a solubility chart on the AP chemistry exam. They're kind of expecting you to know that nitrates are soluble, and so that would be aqueous. So, little word of advice. Silver chloride is insoluble. Chlorides are generally soluble except for three exceptions: silver, lead, and mercury. So that's the rule for chlorides and bromides and the rest of the halides generally, except fluorine. Sodium nitrate, also soluble, so that's aqueous. Okay, so because they're aqueous, this one and this one, I actually am going to write them separate as separate ions because they're now independent of each other, floating around the solution, looking for a relationship. All right, silver chloride has already found its relationship. And so I'm going to write that together. So here's the deal. We are now going to then say, all right, look at the sodium. Starts by itself, ends by itself. Let's get rid of it. Didn't do anything. Nitrate, start by itself, end by itself. Didn't do anything. And so what I have when I write the remainder is just the ions that actually did something. Yes, there's other ions here, but silver and chlorine are the two that got together, and that is my net ionic equation. Okay, let's check out a gas-forming reaction. A gas-forming reaction is a double replacement reaction similar to the one we just did, except one of the products is H2CO3. You'll see this fairly regularly. H2CO3 is carbonic acid, and that decomposes immediately to produce water and CO2 if it's not held under pressure like in a soda can or something like that. So let's look at an example. Here we have hydrochloric acid becoming sodium carbonate, sodium chloride, and here's our carbonic acid, which will immediately break down into those two things. Okay, now I could take the time to split these apart into their ions, and why don't we do it for this one? We'll skip it for the next one. Cl minus. Here's this one: 2 sodiums and a carbonate. Notice I'm putting charges: sodium and chlorine. Now these other two are actually molecules, so those are together, and that is good. So we're going to balance this. We'll need a couple there and a couple here to balance that out. Okay, what are the things that are together or separate on both sides of the arrow? We have 2 sodiums and we have 2 chlorines, so they're going to go away. The hydrogen started out aqueous but ended up in liquid, so it changed. The carbonate started out aqueous and ended up as parts of 2 compounds, so it changed. It's not over here anymore. The sodium and chlorine go away, and our net ionic equation is there. It looks a little different from our precipitate equation, but that's how you do it. Separate the aqueous ions. And here's another word of advice. Take some time before the AP exam to review your 6 strong acids. Some people will tell you there's 7 caloric, but there's 6 strong acids: hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric. Make sure you know them, because when they appear in a reaction, they are going to be separated completely into their 2 ions. They dissociate completely. Weak acids will not dissociate completely and actually should be written together in a net ionic equation. We'll see an example of that in just a sec. So we're going to separate that. This is also aqueous. So if you notice, the chlorine is aqueous on both sides of the arrow. And so we get rid of it. Magnesium is a solid, turns aqueous. That's a change. Hydrogen started aqueous and ended up as a gas. So that changed. So my net ionic equation, let's write it. I'm going to have to get a new pen here soon. And that would be my net ionic equation. Incidentally, I saw this one in a multiple choice question recently, and here they are asking you, what is the net ionic equation for this type of reaction? They give you all the choices, but we have to laser focus and say, hey, if these are aqueous, they're not together anymore. So we separate them and get rid of them, and this top one, A, is the one we just took a look at. All right. So take a moment and see if you can pause the video and write the net ionic equations for these 3. Okay, and if you were able to come up with these 3 net ionic equations, you are doing very well with net ionic equations. First, OH plus H plus makes water. That is the net ionic equation anytime a strong base and a strong acid get together. This is a strong acid, so chlorine is a spectator. This is a weak acid, though, hydrofluoric, so a base plus a weak acid. Keep that together, because during the reaction it's going to lose its proton, which it hadn't already, and that's a change, so we have to include that. And finally, we have the production of a gas. Hydrogens plus sulfides make hydrogen sulfide, and the sodium and nitrates both start out aqueous and end up aqueous, so they are out of here. All right, let's take a look at a couple quick questions. Lots of times you'll be asked questions about types of reactions, and they will be written as net ionic equations in most cases. So which of the following chemical equations represents a precipitation reaction? We need to note something that is a solid coming out of an aqueous solution. That's the key. This first one has a solid forming, but it's not out of an aqueous solution. It's from a solid and a gas. The second one has the ions in aqueous solution making the solid, and so that is my answer. We'll go with letter B on that. Next one, which of the following chemical equations represents an oxidation-reduction reaction that is also a synthesis reaction? So we'll get to oxidation and reduction in just a moment, but here's some net ionic equations. Precipitation reactions are not net ionic or not redox. They're just ions joining up. They're already there and they're not changing. But magnesium going from elemental 0 charge into a compound that's oxidized, this is reduced, and does look like a synthesis reaction, and so we're going to go with that one. All right, your turn for a pause the video moment. I have 2 of them on this slide. We're choosing from the top 5 choices up here. We're looking for a precipitation reaction and a reaction in which the same reactant undergoes both oxidation and reduction. Take a moment, pause the video, and see if you can get this one. Okay, so for the first one, letter C, we've got aqueous ions forming a solid. And in this one, it's letter B because we have bromine starting at 0, but ending up at -1, this one, and +5 over here. And we're going to be talking about assigning oxidation states in just a moment. Up next, we have section 4.3, which is representations of reactions. And there are 2 primary ways that reactions are represented. One is with a balanced chemical equation, and 2, with molecular models. Now, molecular models can be a useful tool for visualizing physical and chemical changes. As you look at them, be watchful for models joining together or breaking apart, as these indicate chemical changes. If models are simply moving around, this indicates a physical change. And by models, I mean usually just a drawing, like a circle, indicating an atom or a molecule. Let's look at a couple examples. For example, this one. This one actually has 4 models in it, representing 4 different changes that could occur. And your big question you have to answer to yourself is, are these two combined, are these models, these circles, combining into new groupings, or are they just simply moving around? Are they representing a phase change? So, for example, I see models that are widely separated and then they become orderly and stacked, but they're not really combining with other elements. They're all the same. And so this, to me, represents moving from a gas or a liquid into a solid. That's a phase change or a physical change. Here we have the opposite, a solid, an orderly arrangement moving apart into the liquid or gas phase. And so again, we've got some sort of vaporization going on. Here we have molecules with 2 different types of models in them, but they're simply just moving around. They're not actually reorganizing themselves into new groupings. So we just have a physical change there as well. But down here, we have groupings. These probably represent water molecules, and they have now changed into new groupings. And that right there would indicate a chemical change. So we could write a reaction for that, 2 of these becoming 2 of those and 1 of those if we needed to. All right, let's look at another one. Again, if you're looking for chemical change, you're looking for atoms and molecules regrouping. So here we have, the question is this a chemical change or a physical change? So I'm looking over here, I see these pairs of greens, and then these molecules here, probably methanes or something. And then, yes, they have changed into these new groupings, which to me look like baby octopuses, which is kind of fun. But yes, there's definitely new groupings here, and that is a chemical reaction. All right, let's pause the video just for a moment and take a look at this practice. Classify each molecular diagram as a physical or chemical change. See you back here in a couple seconds. Okay, and if you guessed that this first one is a physical change only because the particles are not changing, they're just spreading out, that is correct. And down here again, we have that chemical change happening. All right, I like this diagram because it's trying to show both physical and chemical changes all at once. And so there's 5 different changes that are happening here. Let's try to decide what is going on in each case. So here I've got pairs of reds and blues, and then they're rearranging slightly. Okay, so that to me is a chemical reaction. These 2 are combining into those. Okay, that's number 1. And then going from number 1 to number 2, notice that the molecules are not changing, but I am separating them. So that would be a physical change, just a separation of the 2 components of that mixture. So we separated them. And then what if we go from here to here? I can see that the pairs of models are breaking down into singles, and so that would be a chemical reaction, probably a decomposition reaction. And here, these molecules that we separated out in process number 2 are now stacked in an orderly array. So that indicates to me that we're not changing anything, we are just freezing it and putting it into the solid state. So that's number 5. I skipped number 4 there for a second. If I were to take these molecules and move to here, we would get groupings of new molecules, and that would be a chemical reaction as well. All right, now let's take a moment and look at a molecular model and actually write a chemical reaction from it. So sometimes we have to do that, and we have to convert one of these into a balanced chemical equation. So if I'm looking at this model, I'm seeing these pairs of yellow things and pairs of these purple things. I happen to know this represents iodine. That's kind of the color of elemental iodine. So iodine is going to be one of my reactants. And the chlorine, the yellow is representing chlorine here because chlorine is a yellowish gas. And those are diatomic. Take a moment and just remind yourself of the 7 diatomic elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. When you see them by themselves, they are diatomic in elemental form. They spell the fun word Brinkelhoff, if you like those mnemonics, and that's always a fun way to say it. All right, so moving from here to here, though, they've regrouped. And I can see we've got these molecules where there's 1 iodine and 4 chlorines in them. ICl4. Okay, now there is one iodine pair that is not reacted, and that's simply because the chlorine ran out. I use this model in my limiting reactant video. You could find that under reactions, and also there's a playlist on stoichiometry if you need help with limiting reactants. Last thing I'm going to do is I'm going to balance this thing. I see 2 iodines here and only 1 there, so let's put a 2 there. And now I have 8 chlorines over here, so I need a 4 there. And so that would be our balanced chemical equation from a molecular model. Okay, you try one. It's a simple one. Take a moment and see if you can guess the balanced chemical equation for this reaction. Back in a second. Okay, and if you wrote down N2 plus 3 H2s, making 2 NH3s as your balanced chemical equation, you've got that right. That's kind of the process that we would use to go from a molecular model into a balanced chemical equation. All right, and you're likely to see questions about general chemical equations that have already been written. So you'll have to know how to balance them. If you need to review that before the AP chemistry exam, go ahead and do that. Here's a typical question. Take a look at the balanced chemical equation, and the question asks, what is the coefficient for H3PO4 once this thing is balanced? So we take a moment and we balance it, and let's pause the video and see if you can balance this and come up with the correct coefficient for H3PO4. All right. Balancing equations is kind of like the bread and butter of chemistry, so hopefully you've got a lot of practice doing that. If you did a 1, a 4, and a 3 to balance it, congratulations, and that would mean the correct coefficient is. And for our last one in this section, here is another unbalanced chemical equation. Take a moment, pause the video, see if you can balance it, and come up with the correct coefficient for oxygen. All right, and when I balanced it, I first got 14, but then I realized I was wrong. So it ends up being 12 for the oxygen. And this is because over here with 10, a 1, and a 6, we have 28 oxygens that need to be balanced on the left-hand side. There's already 4 there, so really I only have to come up with 24 more in that spot. So that ends up being letter C. So congratulations if you got that one without doing what I did and making an error. If you're studying for your AP chemistry exam, hopefully by now you've done a lot of stoichiometry. You're probably in your second year of chem, so you've had a lot of time to do these. Stoichiometry problems are kind of like our bread and butter when it comes to calculating things in the laboratory and on paper. And there's not enough time to do all the variations of stoichiometry in this video. I will say that I do have a playlist on stoichiometry, so if you have to go back to the beginning and start fresh and just learn through several videos, you can check that out. But stoichiometry is here in Unit 4. It actually applies in all the units of AP Chem as well. Stoichiometry is the study of quantities that go into and come out of a chemical reaction. The heart of any stoichiometry process is the mole ratio, that balanced chemical equation. How many moles of this, how many moles of that? So X moles of reactant in, Y moles of product out. It varies depending on the prompt. General stoichiometry steps, though, are pretty much always the same. Convert whatever you have into moles. So there's a number of ways to do that. Use the mole ratio, that's the heart, to predict the moles of the other thing you're interested in. And then convert that amount to a desired unit, like grams or liters or volume of a gas or that kind of thing. So I like to say, yeah, there's a million variations of stoichiometry problems, but they all tend to do pretty much the same thing. So they're all kind of the same. So while some calculations involve up to 3 steps, other questions will ask you what happens if the amount of reactant is changed. So if the reactant is doubled, the product should double, all other things being equal. If the reactant is halved, the product will be halved. If a reactant is doubled but the limiting reactant remains unchanged, then your final product is going to remain the same as well. So some general ideas about that. And we're going to see some problems. There are a million stoichiometry maps on the internet. So if you search for one, you'll see a bunch. Find one that you like, and hopefully maybe you have one already. But in generally, there's a number of ways you have to get to moles. You might have grams, you might have liters of a gas, you might have the number of particles, you might have the volume and molarity, all kinds of ways. But the idea is you just got to get to moles. And then do your mole ratio, moles of what you want over the moles of what you have, and then convert it back to what you need to. So Like I said, there's not enough time to do all stoichiometry problems here, but let's start with some. And I'm going to do them pretty quickly, and we can pause the video so you can try them. First, pause the video moment. According to the reaction represented above, about how many grams of aluminum are necessary to produce a half a mole of hydrogen gas? If you'd like to pause the video, take a moment and do that, and in 2 seconds, I'll show you the solution. For the sake of time, I've already worked out the solutions. So in this case, I got 9 grams. So half a mole, and then the mole ratio is 2 moles of aluminum for every 3 hydrogens multiplied by the molar mass, and I got 9 grams of aluminum. So hopefully you got that. Next one in rapid succession. Here is a redox reaction. Nice thing, though, is it's already balanced, so great. According to the balanced equation above, how many moles of HI would be necessary to produce 2.5 moles of iodine? Take a moment, pause the video, and I will show you the solution in just a second. Now, the actual problem is only one step, because I knew how many moles I had, this many, and I want to know how many moles of this. So 2.5 moles of iodine, 10 moles, and 5 moles. So there's 10 moles of this are needed for every 5 moles of that, and I got 5 moles of HI. Now, I did have to double check. I just wanted to make sure I got it right. Using the moles of the other 2 things they gave me, I wanted to check to see if those were excess reactants, that they're not going to run out first and change my answer. But with 4 moles of KMNO4, I'm able to make 10 moles of iodine. That's plenty. I'm only making 2.5. And with 3 moles of H2SO4, I can make 5 moles of the iodine. If I had enough of the other stuff, those are possible. Those are both bigger than what I'm making, and so these are excess reactants, and I can just ignore them for now. If at any point you have questions, you can always send them to me in the comments. Here's another one. Okay. According to the balanced equation above, how many moles of ClO2 are needed to react completely with 20 milliliters of 0.2 molar KMNO4 solution? So here we have a volume and a molarity. Take a moment, get it to moles, apply the ratio, and see what your answer comes out to be. You can hear all the pencils furiously scratching out there. Turns out I got an answer of A on this one, 0.003 moles. So let's walk through it. 0.02 liters, you got to change it into liters because the molarity is in moles per liter, so make sure you do that. And then we apply the ratio. 3 moles of this for every 4 moles of that, and it worked out for me to be 0.003, and if you got that, then we're on the same page. All right. Next one. All right, so the next one I chose this one to point out I guess a shortcut, but also something that you're likely to see, and it kind of messes people up sometimes. A 1 liter sample of an aqueous solution contains 0.1 moles of NaCl and 0.1 moles of calcium chloride. So we got 2 things that are producing chlorine in the solution. What's the minimum number of moles of silver nitrate that must be added to the solution in order to precipitate all of the chlorine as silver chloride? Take a moment and think about how you would do this and like self-assess, I guess you could say. And then I'll show you what I ended up doing. Hopefully you pause the video on that. This is the thing that I just wanted to highlight. First, with 0.1 moles of sodium chloride, that's going to give me 0.1 moles of chlorine because there's 1 chlorine for every sodium chloride. 0.1 moles of calcium chloride is going to give me double that because there's 2 chlorines for each one. Now, the thing I want to highlight is that once something dissolves and separates into those ions are now independent of each other. They're independent of where they came from. And what we really just need to know is the total number of chloride ions in that solution, whether they came from sodium chloride or calcium chloride. 0.3 is the total. And because each chloride ion needs a silver ion, 1-to-1 ratio, that means I'm going to need 0.3 moles of silver also needed. Okay? And so hopefully that made sense. All right, 2 more to go. All right, first one, and these are going to be limiting reactant questions. Limiting reactant questions. So when 8 grams of this and 92 grams of this are mixed together and react, what's the maximum mass of H2O that can be produced? So when you're doing limiting reactants and you have amounts of all of them, what you have to do is make a prediction for both. You have to start with all your amounts, make that prediction to the water or whatever it is you're finding, and then choose the smaller amount. That smaller amount is your maximum theoretical yield, because after that amount is being made, one of the reactants has been used up. So we have to do this twice. I'll show you mine. If you want to pause the video and try it, you can. I'll show you mine, and that is this one. I got a total of 9 grams of water. 8 grams, I changed it to moles, and then I applied the ratio. 4 waters for every 2 N2H4s, and I got 0.5 moles of water. And I stopped there for a second. With 92 grams of N2O4, 92 grams per mole, that's 1 mole, and I multiply by 4, I get 4 moles of water. So with this, I have enough to make 4 moles. With this, I only have enough to make a half a mole. That's how we interpret that. And then because it's a half, that's the smaller amount, I quickly changed it into grams, and it worked out to be 9 grams of water. All right, are you ready to try one on your own? This is our last stoichiometry problem for today. This is a limiting reactant problem again. Take a moment, pause the video, read it through, and see if you can find out how many moles of NO2 gas can be performed. All right, good job on that. I came up with 0.015 moles because I already had moles of silver, so I just applied the ratio, 1 to 3. And I had to find the moles of HNO3. So liters times moles per liter gave me moles, and then it's a 1 to 4 ratio. That gave me the smaller number of moles, and that's my choice in the answer. So hopefully that helped you review some stoichiometry. Spend some time doing some more before the AP chemistry exam too, because you are guaranteed to see a bunch of stoichiometry on the exam. Next, we come to a quick little unit topic on titration. Introduction to titration. So hopefully by now you've done a titration or several. My classes usually do several during the course of both honors chem and AP chem. But titration is the process for determining a quantity about one solution by adding a known solution to it, hopefully very accurately. And just a quick side note, I do have a video in Unit 9 playlist called Tips for the Perfect Titration. And it's one of my most popular videos. I go through the whole process start to finish and offer some tips for you to do a really good job with your own titration. So feel free to go check it out. Usually these are acid-base neutralizations, but it could be precipitation or redox. We do one of those in my class. Things you're trying to determine. Sometimes it's a molarity, a molar mass, or a pH. These determinations usually involve 3-step stoichiometry calculations. So now that we've done stoichiometry, we'll be applying that here. Typical titration setup involves having a burette filled with some solution. We call it the titrant. Usually we're going into a flask. It could be a beaker or some receptacle down here. And we read the initial volume and the final volume to find out how much goes in. And this is always a stumbling block for people who start doing titrations for the first time. The burette is numbered upside down. So 0's at the top and 50's at the bottom. And then there's extra space where there's no markings. And that extra space throws people off because they think if it says 46, maybe they're saying it's 46. But what do you do about that? The important part is not how much volume is down here, but how much actually goes into your flask. The final minus initial of your 2 readings. And you're likely to be asked a question where you're going to have to read a burette on there. We usually have some sort of way to get a known amount into our flask. Maybe it's a pipette or maybe it's weighing out something that's there. So let's do some vocab right away so you can speak the language of titrations. Titrant is the liquid being added to the unknown. That's what's in the burette. We call that the titrant, whatever it happens to be. The burette, of course, is the item of glassware that's made for dispensing those accurate amounts. The endpoint, or the equivalence point, you can call it either one, is the point at which the number of moles of titrant equals the moles of the unknown. And the unknown is something that we would call the analyte, whether it's a solid or a liquid. That's the thing that's down there being tested. All right. Like I said, I have a longer video about this, but here I summarize the tips for better titrations. First, you're going to rinse the burette with water first. Get everything out of there that somebody else might have left in there. Then, this is key, you're going to rinse it with a small amount of the titrant, because if you rinse it with water, there's going to be drops of water in there, that are going to cause you error. They're going to dilute whatever you put in there. So rinse it with the amount of the titrant, get rid of it, then fill your burette. And then let a little bit of air out of the tip. Just let some drain through so that the tip is full of your titrant. This volume does not have to be 0 at the top. So a lot of people need it to be 0 right at the top. But just drain a little bit out. Your starting volume might be like 2.3 milliliters. But just go with that. Read the burette to its maximum accuracy at the bottom of the meniscus. So if your burette goes to the 10th place in milliliters, you should report to the hundredths. Or if it goes to the hundredths, give it to the thousandth. Make sure to estimate. Practice adding 1 drop at a time near the end point. Just it takes practice, 1 drop at a time. Then when finished, you're going to rinse the beer out with water, and we store them upside down and open for a day or two to let everything drain out and so we don't clog the tip on that. All right, let's look at a couple of quick questions, starting with one that does not require a calculation. A student pipetted 25 milliliter samples of hydrochloric acid and transferred each sample to an Erlenmeyer flask, diluted it with distilled water, and added a few drops of phenolphthalein. Each sample was then titrated with the sodium hydroxide solution to the appearance of the first permanent pink color. Hopefully you've had the pleasure of working with phenolphthalein. The following results were obtained. Which of the following is the most probable explanation for the variation in the student's results? Okay, so don't choose the answer where the student misreads anything. We're assuming that the student read it as properly as they could. So human error, don't go there. A different amount of water was added to the first sample. When you're doing titrations, you might know this by now that the amount of water that you add doesn't really matter. It's the moles of titrant and the moles of analyte. Whether they're in 100 milliliters or 200 milliliters, it really doesn't matter with the water. The pipette was not rinsed with the HCl solution. Well, the pipette is a standalone thing. It's calibrated very well, and there's no weird nozzle or tip that has to be factored in to it. You just fill it up to the mark, and assuming we do that pretty well, they're pretty accurate. But if you don't rinse that burette with your sodium hydroxide solution, then you have those drops of water, which dilute it, and you have this variation. So of these choices, I'm picking A on that one. Now, the next one is a calculation question. It's a stoichiometry calculation with the initial and final burette readings. And an antacid tablet containing magnesium hydroxide is titrated with 0.1 molar solution of nitric acid. The endpoint is determined using an indicator based on the table above. What is the mass of magnesium hydroxide in the tablet? Take a moment and pause the video and use your stoichiometry prowess to see if you can get an answer. And when I did it, I got an answer of A. So, volume used, 22.17 minus the 2.17. 20 milliliters went into the flask. Change it into moles, liters times moles per liter, and then it's a 2-to-1 ratio. Notice how there's 2 OHs in here? They're going to need 2 acids to neutralize that. And so you had to kind of think about the mole ratio there, multiply by the molar mass, and I got 0.0583 grams of magnesium hydroxide. If you're still here watching this video, I thank you, and I want to encourage you that we only have 2 sections left to go. First, we have 4.8, Introduction to Acid-Base Reactions, and we'll finish with redox. Acid-base reactions are reactions in which there's an exchange of protons from one species to another, and that's a hydrogen ion. The acid donates the protons while the base accepts them. Quick side note, Unit 8 is all about acids, bases, and buffers, and you get really deep into them here in Unit 8. Here, we're just going to give a brief overview of the types of reactions. All right, so let's define what an acid or base is. You probably have heard a couple of different definitions. The second one is the one we're going to use most often. But Arrhenius once said he noticed that acids have H3O plus in them. So he said a substance that produces hydrogen ions or hydronium ions in water, that's the acid. And anything that produces OH ions is a base. And that's great. It's a nice blanket rule. But Bronsted and Lowry defined them as the things that give protons away, that's the acids, and the things that accept those protons are the bases. So it's all about the exchange of protons. Then we just have to identify what is doing what. All right, quick side note, there are 6 strong acids. Take a minute before the AP exam and learn these. They're not going to give you a list of these, but they're expecting you to know the 6 strong acids and that they will 100% dissociate. That's what makes them the strongest, not their pH or anything else. It's the fact that they give away all their protons. All right. All the other acids besides these are weak acids, and they should be written together. These should be written as dissociated because that's how they are in their solution. So weak acids like hydrofluoric. I think it's interesting, by the way, that hydrochloric, hydrobromic, hydroiodic, the friendliest acid in the world, they're all strong. But hydrofluoric is weak, and you might wonder why, because fluorine is in the same column as those. But fluorine is weak because even though its bond is very, very polar, its bond is also very short and strong. And so the fluorine hangs on really tightly to the hydrogen and only dissociates about 5% of them. All right. General types of acid-base reactions. The biggest one is the neutralization one. Acid plus base makes water and a salt. Try to make that your mantra, because people get on the right-hand side, they start drawing other things besides water molecules like H4O or HOH3 or something. It's just water. So laser focus. Acid plus base makes water and a salt. Acid plus carbonate, we saw one of those, is water, a salt, and some bonus CO2. And I'll show you an example of this one where nonmetal oxides are used to make acids. All right, neutralization examples. Going quick. Note, each one of these has an OH and an H in there somewhere. And look what my products are doing. Each one of them, I just made water and then a salt with whatever ions that remain. So just make it water. Don't get anything weird about it. And then, of course, you have to balance the charges. And sometimes you have to balance. Because this is a diprotic acid, we need 2 OHs to balance that. All right, other reactions you should know about. When nonmetal oxides react with water, they actually make an acid. They combine. And for example, SO2, this could be done with NO2 or CO2 plus the water. Put it together, you make an acid. Those will dissociate, so you might want to write them as H plus and HSO3 minus. And when a metal oxide reacts with water, it tends to produce a base, a hydroxide base. And so sodium oxide and water makes sodium hydroxide. And again, because it's soluble 100% of the time, I would write them as separate ions. All right. You might also need to know about, you're going to need to know about conjugate acids and bases. So conjugate acids and bases are what we call the acid and base for the reverse reaction. Lots of acid-base reactions are reversible. And so on the forward reaction, you'll have something donating a hydrogen. That's the acid. Water here is the base. And then, but if we wanted to reverse the reaction and have the H3O plus give the hydrogen back to this HCO3, that would act like the acid. So a couple of ways to think about it. Whatever is the acid becomes the conjugate base. Whatever is the base becomes the conjugate acid for the reverse reaction because the proton has to be swapped back. All right, let's look at a couple of quick little examples, not calculation examples. We've done a lot of those. So you'll need to know about conjugates. Which of the following is the conjugate acid of NH2 minus? So if you're trying to visualize the conjugate acid, think to yourself, this must be a base then, and it must accept a hydrogen to become the conjugate acid. And we're just going to add one hydrogen to this and make it NH3. All right. And here we have a reversible reaction. HSO4 in water makes H3O plus and SO4 2 minus. In the equilibrium represented above, there are 2 species that act like bases. One for the forward, one for the reverse. See if you can find them. Pause the video and I'll be right back. All right. So the forward reaction, the water is acting like the base because it's accepting. And for the reverse reaction, this would have to accept back. So we're looking at water and SO4 as our 2 bases. That's choices 2 and 3, which is letter D. At long last, we've come to our final topic for Unit 4, and that's redox reactions. Again, just a brief introduction, not all the details about galvanic cells and things, which will come in Unit 9. So redox reactions are reactions in which there's not an exchange of protons, but an exchange of electrons. And get a couple of vocab terms out of the way. And oxidation is the term we use for the loss of electrons, something giving them away. and reduction is the gain of electrons, something taking them in a reaction. A redox reaction occurs when one or more electrons is transferred, one substance loses while another gains. So keep those terms together. Just a quick little example of sodium giving an electron away to become positive, chlorine picking up an electron to become negative. So if you see a change in charge, that indicates redox. Quick definitions you might see: oxidizing agent. The oxidizing agent is the thing that is reduced. So whatever is reduced is the oxidizing agent because it causes something else to be oxidized. Whatever is oxidized is the reducing agent because it causes something else to be reduced. All right, and so in order to figure out if a redox reaction is happening, we have to assign oxidation states. And that's kind of the basic thing that we have to do. And so take a few minutes, and we'll do it right now, and learn your rules for assigning oxidation states. Some elements have lots and lots of oxidation states they could be, so they don't have rules. But other elements do. And you probably have these in your notes somewhere. Here are the major ones. Rules for oxidation states. First of all, if you see an uncombined element, no charge, zero. It's got zero oxidation state. The oxidation state on a monatomic ion, like calcium 2 plus, would be that charge. Okay. Oxygen has a rule. Oxygen is generally -2. It could be a -1 if it's in a peroxide compound or if it's with fluorine, but most of the time it's -2, so you can kind of bank on that. Fluorine is -1. It's just got a rule. And in a compound, it's -1. As an element, it's 0. Hydrogen is usually +1, except in a hydride. That's a metal-containing compound. If you put calcium and hydrogen together, hydrogen takes the -1, and so on. And the sum of the oxidation states for a compound must be 0, and if it's a polyatomic ion, the sum of the oxidation states must equal the overall charge. Okay, so we're going to be assigning some oxidation states in just a moment. And we can quickly introduce the idea of half reactions. Half reactions are balanced equations that show an element that gets oxidized or reduced, how many electrons are gained or lost in the process, the exchange of oxygen and or hydrogen from the surrounding solution. All right. So for example, this overall chemical reaction, iron plus 2 plus copper 2 plus, makes copper and iron, can be split into two half reactions. And we can see that iron is losing 2 electrons because it goes from 0 to +2. Copper is gaining the 2 electrons as it goes less positive, like that. Because you're likely to see half reactions on the AP exam, let's talk about how to write them. First, we're going to assign oxidation state numbers to all elements in the reaction, determine which element is oxidized or reduced. We're going to start by writing the unbalanced equation with the complete terms. We're going to balance the redox active element if necessary. We're going to add electrons to the half reaction on the right if oxidation, left if reduction. So oxidation produces them, reduction uses them up. And they get a little complicated looking because sometimes you'll see oxygens on one side but not the other side, and we have to think about what to do with them. I'll show you that in a minute. Add waters to the equation to balance the oxygens, if any. And then we can balance it with hydrogen terms, either acidic protons or basic OHs, if it's an acidic or basic solution. And then we're going to check to see if the charge balances on both sides of the equation. Let's do a very common half reaction. And I want to show you some pictures that go along with it. So first things first, what if you had permanganate ion that's in solution, and we know it becomes manganese 2 plus. All right, so manganese is going to go from +7 down to +2. So that's getting reduced. So great. We might need to write the half reaction. Well, I can already tell that because it's going from 7 to 2, that's a difference of 5 charges. That means, and it's getting reduced, so it has to pick up 5 electrons. So I'm just going to add those 5 electrons there. Now, some of you who are new to this might be looking at this being like, Mr. Rudolph, how am I supposed to balance those oxygens because they're over here, but nothing's over there? What is going on? Well, we have to recall that a lot of redox reactions happen in aqueous solution, which is the sea of water molecules floating around. They can interact with the reaction. If the solution is acidic, there are protons floating around. They can interact as well. So watch what happens. To follow the steps, I'll just finish this. I can actually add 4 waters to the right-hand side to balance those oxygens. And then I can go back over here and add 8 hydrogens to this side. All right, you might need more of a tutorial on that, but check them out in the other videos. But here's our balanced half reaction. And you're like, how can I just add those things when they weren't there before? Well, imagine the permanganate ion, in order to become manganese plus 2, has to pick up 5 electrons. So there's 1 down there, 2, 3, 4, 5. Okay, it's got to pick up 5 electrons. Those have to be present in the solution. But where do those oxygens go? Well, imagine that those oxygens now break off and just produce 4 waters in the solution that weren't there before, but now they are. They can produce waters like that. And then finally, in order to make those 4 waters over here, I'm going to need some hydrogens. That's where the acidic protons go in. And so we can add them to the left. They're present, so we can use them, and we can balance that half reaction. All right, let's do a couple of multiple choice questions to get us through to the end. And you'll have your pencil handy so you can assign some charges. Which of the following represents a process in which a species is reduced? So getting less positive. So not that one, it's getting more positive. Not that one, it's getting more positive. This one looks like it's getting more positive, going from -1 to 0 and -2 to -2. So that's not really. So this one actually throws a lot of people off. But if you assign your oxidation states, you actually find that in part C, the nitrogen goes from +5 down to +2. So it is getting reduced. The sulfur here is going from 4 to 6. That's oxidizing. But you have to find a single element that is going up or going down. Doing these fast, feel free to pause the video and try them first. In which of the following species does sulfur have the same oxidation number as it does in H2SO4? So we have to assign it here and then assign them down here based on the rules and see which ones match. Pause the video if you'd like. And I got letter D on that one because it starts out at +6 over here, and in letter D it is also a +6. So hopefully you got that. All right, next one. Which of the following is true regarding the reaction represented above? So they give us 4 choices, and it might take a minute to get through them all and assign all the states. Which of those 4 choices is appropriate? Take a moment, pause the video, and meet me back here in a second. Turns out when I assigned all my oxidation states, I found the oxidation number of selenium went from -2 up to +6. And so that matched choice D. The others did not match at all. And finally, here's our permanganate half reaction combined with a bromine half reaction. And they're put together. How many electrons are transferred in the reaction represented by the balanced equation above? Okay, so if we go back to our original half reaction, I found that 5 electrons are picked up by the manganese as it goes. But when the whole thing is balanced, more of this in Unit 9, 2 permanganates are doing it, each losing 5 electrons, gaining 5 electrons. So that's a total of 10 electrons. Wow, that was a lot of information for Unit 4. If you're still here, thank you. I hope you found it helpful. If you have any questions, please send them to me. And in the meantime, happy studying and have a great day.